Okay, so this is going to be our first video for the course, and it's going to be in regards to our first presentation, the cell. Obviously, there's a lot to talk about, but I don't want the video to be extremely long, so I'm going to emphasize mainly the principles. I also think that when you learn for the exam or learn for life, please learn for life first. Uh, and especially with anything that has to do with function, thus meaning physiology and exercise physiology and pathophysiology and so on, anything with physiology in it, the principles are extremely important, and when you understand them, it becomes easier. So I have a few points to discuss, and they're written within the presentation, and maybe it will help you understand better what is written there. I'll just give a fair warning. The video will not be enough to learn to the exam for. Just wanted to put that out there and make sure that you're not making that mistake. Okay, the first point is communications. When it would be impossible to create homeostasis and survive as we are built and function without the cells being able to communicate between them. And communications at the cellular level and between cells is huge. It's huge. We tend to think about communications between the brain or the nervous system and other organs, but actually very important communications are between cells. And the cell has to invest a lot of time and energy and abilities in those communications. So it's kind of like text messaging that you continuously share information, because sharing is caring, and that is an important, very, very important part of survival, and we understand that it's not only about giving orders, rather than sharing information and letting know your neighbor what's going on. So that's a very important part, and there's an explanation about it in the pathophysiology presentation about the cell. So that's number one. It's extremely important, and I hope that you already know this. I actually hope that anything that I say in this video you already know, and if not, we'll deal with it. One of the first laws in nature, as nature is that the structure influences function, but not only that, the structure must be according to the function that you want to achieve. And that's why you always learn anatomy before physiology, and I truly believe that doing it any other way wouldn't work, be hard to understand, and you wouldn't be successful. So when you look at a structure of something, you understand how it affects function. And I want to give you an example from physiology. When you look at hemoglobin, which carries oxygen, not only but does carry oxygen, which is very important to the cell and to our ability to function as humans. It has 4 hem units that allows one hemoglobin to carry 4 units of oxygen. When you look at the oxygen carrier within the muscle, we're talking about myoglobin. It only has 1 unit of hem. That means that when hemoglobin within the blood, within the plasma, is offering oxygen to the muscle can only take 25% naturally, because it's 1 out of 4. So that is, I think, a classic example of how structure, or the number of units that a protein in this case has, affects function, because obviously that means that the efficiency just went down to 25% just because of that. So structure and function. And we tend to look at anatomy as something not important, because we think that the physiology is more important. But physiology could not exist without anatomy. And every time there's a picture or figure in the book relating anatomy, read it, look at it, understand it, because it's going to affect function. And it's really, really important to understand too, as I'll emphasize later on, in regards to loss of function or alterations to functions that leads to diseases. The third thing that I want to tell you, and it kind of I kind of said it in the presentation, and I'll always say it, and they've used the word waste. The word waste has a negative how would I say this, connotation perhaps to it, and I do not believe, out of all of my studies during the years and experience, that there's such a thing as a bad substance and a good substance. Don't use that. Bad and good, waste. Don't use that. Don't use that. You can use unneeded. You can use metabolites, whatever you want. I don't believe in using bad and good, and my advice is don't use it. Why? For instance, cyanide. Cyanide is a poison. So does that make cyanide bad? No. Why not? In the Krebs cycle, we actually use cyanide, and without that cyanide, the Krebs cycle would not be able to perform its duties and function. And without the Krebs cycle, you know what happens to the whole aerobic pathway. And if the aerobic pathway is not working, then you have a problem. Obviously, you definitely have a problem. This is annoying me. Okay, here we go. All right, so don't think in regards to good and bad. Something that is bad or has a negative influence in one place might have a positive influence in another place. All right, the same goes for lactic acid and so on and so forth. Part of survival in nature is about movement. It's either gross movement, mechanical movement that we call the movement that is generated by skeletal muscles and bones and tendons that are connecting them and so on and so forth, and by chemical movement, meaning fluids, solids, solutes, and so on and so forth. Without movement, we die. So we have to understand that. And the body is built for movement. The body relies on movement, but at the right amount, at the right time, to the right place. And obviously the key word is the right. When something is not right, then trouble starts, and they can actually occur really, really fast. Let's talk about respiration. Respiration is also divided into mechanical respiration and cellular respiration, exactly like movement. Mechanical respiration obviously is the mechanical work of the lungs and the respiratory muscles. And cellular respiration is actually the utilization of oxygen within the cell in order to produce energy. Alright, so one of the important things within the cell to understand, and we talk about it, it's there, but we don't always understand the meaning of it. And I'm talking about location within the cell and the needs to have compartments. So we kind of say, yeah, it's surrounded by a membrane. Sounds really easy, but by saying that, you're actually saying a lot. That means that biology, the cell, has developed in such a way to need to make sure that only specific substances enter that area. The easiest option to explain is the fact that anaerobic pathways are located in the cytoplasm, while the aerobic pathway is in the mitochondria, which has a membrane. So the substances cannot mix, and only specific substances and factors needed for aerobic energy production go into the mitochondria, and that's huge. So when you look at the cell, going over the presentation in the book, notice that, understand how important it is. Energy is everything. Energy is the way to pay for living / surviving. Energy is like money to us. The same way that we conduct ourselves with money, the cell wants to conduct itself with energy, meaning that we prefer, if possible, to get a product or a result, an outcome, without paying, right? Hey, you'd like your degree to be free, but it's not. And there are things that you have to pay for. Naturally, when you conduct a market analysis, the bottom line is to try and see if you can get a certain product at the lowest price, but you want the same product, right? So that would be efficiency, and the body, one of the classical responses called adaptation to exercise and to anything in the body is energetic efficiency. So we want to pay less and achieve the same thing or achieve more. Oxygen, by definition, is energy efficient. You know very well, learning the pathways, the metabolic pathways, that oxygen produces the most energy even when you're breaking down the same substance, substrate, relatively to anaerobic options. And it can grow up to crazy numbers when you compare proteins and metabolism, catabolism of lipids. Cascades. Nothing lives within itself. There's very few examples that a process includes one reaction, and usually it's like a post on Facebook. People start sharing, people start liking, and it's viral. And when you start a cascade in the cell, it has multiple phases and reactions and can have multiple outcomes. The more reactions that you have in a cascade in a process, in order to achieve a certain outcome, the more chances that something will go wrong there are, the more chances of having some kind of disease or disorder you have. A cascade, by definition, is a set of reactions that must happen one after the other in order to achieve a certain outcome. Right? Direction. There are diseases that originate from within the cell and expand to the level of tissue, organ, system, and supersystem. And there are diseases that can start out mechanically from outside of the cell, but at the end will affect the cell. So that, for instance, would be some kind of obstruction, some kind of mechanical force affecting the body. Anything that is environmental from outside of the body, like toxins, gases, pollutants, and so on and so forth. Let's talk about cell growth. Cell growth is about a couple ideas. Simple principles. A, you have to have the budget and the means to grow. Let's say you want to add a room to your house. You have to have the property, right, the space, You have to go and buy everything that is needed to build the house. You actually have to do it, so it's a lot of work. So if the conditions in the environment, either the outer environment or the inner environment for the organism or the animal or of course humans and so on and so forth exists, that allows cells to grow and develop. Part of the ability to grow is the ability to conduct maintenance to the cell and to repair damages if they occur. And damages and injuries are part of life exactly like anything else. So repairing is part of it as well. A cell that does not have the conditions to grow, a cell that cannot conduct maintenance, a cell that cannot repair damage and injury is a cell that is going to die. Alright, so there's a term that's called chemical reactiveness, and that is the tendency, the affinity of certain molecules and ions and so on and so forth to react with other molecules. When we look at the periodical table, the bigger the plus that you have, +2 for instance, the more radical you're going to be. When you have such molecules, when you have such ions that are in need of 2 electrons, that's like someone that is starving. Take someone that hasn't eaten for a few days and put food in front of that person, and you see abnormal reactions. That's that radical reaction, that radical behavior that you see. And the same goes with ions. Ions that are electrically charged, especially those with the +2 level, the cations, are starving for electrons. And I'm using the word starving, although it's not exactly a word in chemistry, because I want to use that analogy. They're starving for electrons and they'll do anything to get them. And by saying anything, that means that they are reckless, they are radical, they're just looking for trouble, chemical trouble, and that's why they're so dangerous. If they are dangerous, you want to remove them. Exactly like you take a criminal, which is regarded as defined as dangerous, and put them and lock them in jail or prison, and you make sure that they go nowhere without a chaperone. The same thing goes for these ions. You do not want them traveling around in the body for too long, chaperoned or not confined. So for instance, one example is calcium. Calcium is +2, right? And when left alone, you're in for trouble. Iron, ferrin, the same idea, and so on and so forth. So I strongly advise you actually to go onto Google, search the periodical table, and look at those anions and cations that are unstable, and understand that they must be confined, must be regulated and supervised, and they have the potential of a lot of hazard. And at the end of the presentation, you'll see what they do. You can see what happens when you let them loose, or let them be uncontrolled. Okay. We tend to think about energy only in the terms of ATP, and I understand that, coming from exercise sciences and exercise physiology. Naturally, ATP, has a major place in our hearts. But actually, what drives energetically cells and molecules are electrons. So not everything is about ATP. Electron exchange is a very powerful force driving chemical reactions. And you can see that in the presentation and in the book as well. Right. Speaking about forces, speaking about movement, in chemistry, movement is due to gradients, and the cell is definitely governed by gradients. If you want to break down any mechanism, you want to look at gradients. So we refer to pressure gradients. We can refer to concentration gradients, and we can refer to electrical gradients, electrical charges. We can refer to tonicity. We can refer to osmolarity or osmolality, which is used more likely in clinical fields like ours. And that's what makes substances move. And movement is life. A cell without movement is dead. And I'll probably say that 1,000 times. 999. Alright, let's see. Of course, we are about fluids. It's not random, or it didn't just happen that the majority of our body weight is fluids. Fluids are life, and the cell is mostly made out of fluids. So when you deal with fluids, you're dealing with the cell, which is the most basic sort of life, and you're asking for trouble. Let's just say it that way. And there's rules, of course, to the movement of water and fluids. I think that one of the major things that the principles that you can notice throughout the presentation and the chapter is the fact that function comes in pairs. Do you remember that structure influences and defines function, right? Anatomy, physiology. Let's go to anatomy for a second. When we're talking about kinesiology, we know that around every major bone, especially the elongated bones, we have at least two muscles, right? One usually acts as an agonist and one as an antagonist, and I said at least two. So you know that we have the biceps and we have the triceps. You know that. That's kind of basic knowledge for all of you. But the fact is that it always comes in pairs, right? Why? Have you ever asked yourself why? It's one thing knowing that. Okay, so you know agonist and antagonist. You know that a balanced workout plan will work on, let's say, the chest and the back, right? But why? Because we want balance. And balance is something that the cell sometimes wants. Once again, the cell also needs movement, so we want to have imbalance. But in that case, when we're not looking for balance, we're looking for a certain kind of imbalance. Do you know which kind? Luckily for you, I'm here to tell you. We're looking for controlled and regulated imbalance. There's a difference. Okay? So notice that. You'll see that with all the conditions that might arouse from imbalance. Anytime we use the words hypo and hyper, we're talking about imbalance. Every time we analyze that, what causes hyperalkalosis? What causes hypoalkalosis? And so on and so forth, or acidosis, and so on. You'll always see that there's at least two factors that need to be balanced in order for the system not to go hyper or go hypo. Always at least two. There's never only one. So that can be the game between sodium and potassium. It can be sodium and chloride. It could be hydrogen and potassium. You can also look at it at the level of buffering that we'll talk a bit more about, and the presentation actually includes that. And you'll see that you have two systems working in order to achieve balance. So for instance, when we're talking about CO2 in regard to acidosis or alkalosis, we're playing between the respiratory system on the one hand to the renal system on the other. Always pairs, at least two, at least two. And there's definitely always two major players or factors. So remember that, pairs. Pairs is something that contributes to balance and is a major principle in our field. Look at the presentation. Identify these principles within the presentation and within the book and understand them. It will be impossible to understand diseases without it. All right, it's really important. All right, let's turn the page. Okay, you'll see that in the presentation, some words at some points that have a negative connotation or understanding are in red. And I want to talk about the idea of something that is lacking versus something that is inhibited versus something that is delayed. When something lacks, that is extreme, because there is no option to achieve it. In principle, when something is inhibited, for instance, a receptor, it's not that you can't achieve it, you just have to make a small change, right? So it's about competition. When something is delayed, it's going to happen. It's only going to take a bit more time. So that might be the lack of enough enzymes, for instance. It's not that the enzymes are inhibited and can't do their function. It's just that there's not enough. There's a difference. Okay. So receptors, which are major components that influence function, are lacking. That's a huge problem. When they are inhibited, it can be taken care of. When they are delayed, it's not perfect, but it's better than the other two, if you ask me. Sometimes, when physiology and exercise physiology is taught, no matter by whom, we miss out on a very important principle in metabolism. When we look at and analyze energy metabolism, we're basically playing more or less with carbs, right? Lipids and proteins. At the end of this course, if you haven't understood it already, you will definitely have to understand that it is impossible to separate the three when it comes to metabolism. Impossible. Since metabolism, by definition, is a very materialistic, so-called materialistic way of getting things done in the cell, metabolism is the utilization part of achieving an outcome wanted in the cell. It is impossible that a disease will not affect metabolism, or use it as a means to present the problems that disease develops. The cell has a lot of each and every one of them. Let's talk about it. Carbs are important for energy production, obviously. They are important for signaling, and they are important for defense, for the immune system. The nervous system utilizes only carbs. When you influence carbs for the worse, you are asking for trouble with the nervous system. You want a bit of advice from Iran? Don't mess with the nervous system. You'll never win. It is fast, nasty, and there are so many different things that the nervous system can do to you. So think about it. Lipids. Lipids are important parts of the membrane of cells. They have extreme importance in the structure of the cell, in that compartmentalization of fluids, aka defining what is in the cell and what is outside of the cell, and ways of coming in. You mess with that, you're in trouble. Besides, we also know that lipids that tend to stay within our pipes, within the arteries and the veins, and tend to stick to that vessel, disrupt the natural flow and function of the vascular system, and it can lead to diseases like atherosclerosis and so on and so forth. Proteins. Proteins govern the body. If there is a king to the body, it's the family of proteins. Enzymes, which are extremely powerful and unique proteins, subfamily of proteins. Hormones, which have great effect and powers in the body. Those two are kind of superpowers. Basically, you mess with proteins, you're really asking for it, and we will see that it is, let's say it, extremely unlikely that a disease will not include some kind of problem with proteins, right? That includes their function in the membrane. Once again, the membrane is extremely important to understanding function. When you have a problem with your membrane, you are going to have a disease, usually. Let's talk about adaptation. Let's say that I ask you to lift a bucket full of air. The bucket, just for the example, is extremely light, and I tell you that you can only do it using some kind of cable or thread, okay? Rope, something like that. Naturally, if you were to know that the thicker the cable, rope, / thread that you're going to use will cost you more money because you're only elevating or lifting air, you would take the minimal thickness or thinness, right, needed to do that in order to pay less money, right? But if you have to lift a bucket full of concrete, iron, which weighs a lot, you understand that if you use the same thread for the bucket full of air, it's gonna rip, right? And then your mission is a failure. So you're gonna invest money in having a very thick cable, very strong one, in order to lift it. Let's take this example and understand what we're talking about. We're talking about a mechanical stimulation, right, that is influencing your adaptation to the situation. And I'll explain. The weight of the bucket is the mechanical stimulation. When the weight becomes greater, your adaptation to the ability to lift that load is by thickening the cable. That is exactly what happens when you work with light weights versus heavy weights in the gym. The thickening of the fibers, meaning hypertrophy, right, in this case of skeletal muscles, is the mechanical adaptation to working with weights. When you are running, the stimulation is chemical. The need for oxygen. Thus, the adaptation will be chemical, meaning the utilization of oxygen. And that is why you have bigger mitochondria, they actually fuse together, or they become a lot more efficient, or you have more mitochondria. So adaptation is stimuli specific. All right, that's very, very important, and the same goes for aging. It goes for exercise adaptation. It goes to adaptations to changes in the environment and to disease, and so on and so forth. Let's see. Regulation. Without regulation, you have anarchy. Without regulation and supervision, you have death. Regulation can be from inside the cell, factors within inside the cell, and there's a lot, and regulation can be from outside the cell. One of the key components of developing a disease is losing regulation. All right. Basically, when we look about supervision, regulation, stimuli, enzymes and hormones are huge factors of those. They are both peptides, they're both proteins. And when you say protein, you say DNA. DNA expression, gene expression, by definition, leads to a protein. So it's simply impossible to say protein and not think about DNA, not think about gene expression. Gene expression within itself comes with mutations. And mutations are mistakes. If you remember, this mistake might lead to an advantage or disadvantage. By far, most mutations will have a negative effect. So if we don't want to mess with proteins, we don't want mistakes in DNA, and we don't want mistakes in gene expression, and that's very, very simple. When we're talking about hypo or hyper something, it's relative. Relative to what? To homeostasis. To the right and natural balance of a certain process in regards to a certain substance in the body. So every substance, every process has the right value that produces homeostasis, and two values, one that would go towards hypo and one that goes towards hyper. And you should know that, and that should be easy. Injury. To expect to live without being injured is crazy. I don't know. Doesn't add up. So it's not about if there is injury. It's what injury do you have, and do you have the ability to repair it? And the presentation discusses a few possibilities to injury, which are natural. I mean, you have mechanical injury, you have an immune-based injury, you have a chemical injury, and so on and so forth. Injury in this case means that there is some kind of impairment. It can be acute or chronic. It can be fatal or not, but something has to be repaired. Okay? And when injury ensues, you have imbalance, basically. Let's see. The environment. Think about it. You breathe. By breathing, you are actually connecting to the environment, to the world, and allowing it in. So yeah, there's certain rules and so on and so forth, and mechanisms, but you are bringing in anything that is in the air around you, or the water around you, wherever you are. So naturally, we are creatures, organisms, multi-cell organisms that connect with the environment, and we have a relationship with it, usually for the better. So it is not surprising that we have developed mechanisms of living with the environment, but we are also influenced by it. So the environment is definitely a source of problems in some diseases. Children. Children are, by definition, insufficient, inefficient, fragile, weak. They have less mechanisms of defenses, and they are a lot more vulnerable to any disease and any physiological condition relatively to a mature person. And I would add to that pregnant women, which definitely are more vulnerable at that period. I want to emphasize aging, childhood, pregnancy are not diseases. They are physiological conditions and processes. And there's a huge difference. Okay. Let's talk about dose responses. A magic word. If we knew the right dose responses for everything, if it was the same for every person, life would be really easy, but that's not how it works. And we're talking about hypo and hyper. When we're talking about hemostasis and balance, it's all about dose responses. All right. Of course, dose responses, as you can see in some of the treatments, especially for instance with potassium, if you make a mistake with the treatment, or the physician makes a mistake, and so on and so forth, the nurse, the treatment might take the disease and the condition to a more severe level and lead to death. So definitely treatment has a dose response element to it, and you must know what you're doing. Acute or chronic, I think that's a simple idea and principle to understand. Please forgive me. I have a life too. Um, when you talk, you become a bit dry. So, acute or chronic, we're talking about immediate and short-term effects versus chronic effects. Obviously, short-term effects mean that either the cell has died immediately or fast, or that we could repair it, right? Chronic means that the cell is not dead, but it is dysfunctional, and sometimes it's better to have a cell die than stay dysfunctional. Let's talk about fluids as in a different aspect, the mechanical aspect of fluids. Fluids cannot be condensed. That's one of the mechanical characteristics of fluids, and it has great implications. When fluids are confined, when they are pressured, they pressure back. And I'll tell you something, they don't lose. If you have fluids and they have nowhere to escape to, pressure is going to build up until it becomes destructive. When we're talking about a living body such as ours, and you have accumulation of fluids, hypervolemia, it's going to hurt. It's going to hurt because you're trying to conduct movement. Movement is force. Force tends to be translated to pressure, and when you try to pressure to condense fluids, they fight back. In the middle, we have the nervous system, and when you press on a nerve, you experience pain. So that is why any mechanism, be it inflammation, be it trauma, be it burns, hypovolemia, hypervolemia will be accompanied with pain. Let's see, and of course, when we're talking about a cell, that might lead to the explosion and loss of content of the cell, basically death. Is space a factor? One of the, I think, most interesting questions for me, and it is definitely debated in the scientific community, is does a cell grow according to its functional needs? Pay attention. Does the cell grow according to its functional needs, or is its functional abilities defined by its size? Interesting. How so? The cell is small, and yet you have so many different organelles and compartments and things that have to happen. Do those things depend on the size of the cell, or does the size of the cell change according to the needs? Is cell growth and size hypertrophy, right? Endless? Obviously not, right? At least if you look at all the cells besides fatty cells, the ability to grow is not endless, and thus function is not endless. I think that's a very interesting point, and we'll see that when you rearrange for some kind of reason, when the structure, when things start to move within a cell, because you have a space issue, you're asking for trouble sometimes. Let's see, inflammations. We spoke about inflammations when I gave you a lecture about the about exercise and the immune system. Inflammations are good natural responses that happen quite frequently, and the only problem with them is when they get out of control. And we talked about control, we talked about imbalance. When an inflammation gets out of balance, is dysregulated and uncontrolled, then we have a problem. And inflammations are part of life, exactly like breathing. Right. Aging. So as we said, aging is not a disease, but it may contribute to the occurrence of diseases. There's a difference. One of the major principles and characteristics of aging, and I think it's emphasized in the presentation and in the book, is the occurrence of stiffness. But hey, didn't we say that movement is life? So by that logic, stiffness is the lack of movement. Does that make sense to you? I hope it does. If it does, then it's easy to understand that with age, we lose the ability to conduct movement, to move, either mechanically or chemically, right? We become more stiff, thus we become less alive. That creates, or is, it creates and in turn is created by the lack of ability to maintain a certain status, right? Otherwise you wouldn't become stiff, and to repair it. Otherwise, even if you had stiffness, you would simply deal with it, take care of it, repair it. So obviously that's a major thing in aging. Aging is irreversible. It's gonna happen. I was 22. I remember that day. By the way, it's 25th of January, just in case you care. And time flies by. So yeah, it's part of aging, and you have to understand that. And definitely, we know that dealing with certain diseases when you are an adult rather than an advanced age adult or an old person, it's easier when your systems are matured but you're not advanced aged. I'm saying, by the way, if you notice that the systems have to be mature, because if they're not mature, you'll have problems with coping with diseases as well. As we've spoken of children, for instance, but also teenagers are not mature with their physiological systems. I don't know if you know, but just it comes to mind, and I think it's nice to remind or say, when you look at the cardiovascular system when someone is 17, it's about 85% mature. And within a year, in average, the average person will have those two systems mature, those 15% that are left in average, and become a mature person. Not psychologically. Psychological matureness, by the way, bone matureness and muscle matureness usually occur later on, by the way, by about 3 to 5 years, if you have to know. Okay, sex differences, definitely, yes please. There are differences between men and women. Some are for the better, some are for the worse. With aging, in general, women suffer more, but men die about 6 to 8 years younger due to higher metabolism, higher body average body temperature, which makes a difference, by the way. There is a connection between heart rate and the age that you will die, the length of your life. And men have an average tend to have higher heart rate due to metabolism, and at the same size of the heart, I must say, at the same SV only. That's very important to be accurate. and due to higher blood pressure, and so on and so forth. The unit deals with postmortem. If you notice, postmortem, you're dead. There's not a lot to do about it, with all due respect to everyone. The processes that are explained in the book and in the presentation are simply a matter of time and temperature. I want to explain something about temperature. Temperature is energy. The more energy in a process, the faster it's going to happen, the more radical it's going to be. So for instance, warm water moves faster. Obviously, you'd say, what is he, an idiot? He doesn't have to explain that. We know that ice is cooler and it doesn't move. Not chunks of ice, ice itself. Why? Because the lack of energy is the lack of movement. Abundance of energy leads to more movement, and heat is, by definition, energy. So obviously anything warmer moves more. That is why, for instance, in the presentation and in the book, while discussing drowning, it is said that the likelihood of drowning when the water is hotter is higher, because the heat expands the tissues, it expands airways. When I want to narrow them down and prevent water from coming in, it opens it relatively to cold water, right? And the water are moving more. If the water is moving more, the chances of you drowning are bigger. Does that make sense? In addition, although it really depends on the heat of the water, we know that the hotter the body temperature gets towards 42 degrees Celsius, the bigger the chances of protein denaturation, and that would be the loss of their secondary and third structure and function. So that's not a good idea, right? Metabolism and edema. Edema occurs because of the contraptment of water in a specific area. There are different kinds of edemas and different reasons, and I won't go over them. But when water is trapped, notice the word trapped, they are not available. If they are not available, they cannot take part of metabolism. If you are not taking part in metabolism, by definition, you are not taking part in life. So edema reduces the amount of water, or fluids to be accurate, that are available for metabolism. And when a cell's metabolism goes down, it goes in the direction of death. It doesn't have cell death, of course. It doesn't have to reach cell death, what we call apoptosis, but it might contribute to that. So edema, once again, entrapment of fluids that become non-available to metabolism and decrease the ability to sustain life. Once again, doesn't mean necessarily that every edema leads to cell death, but it definitely is not helping. When we're talking about ions, when you're going over the presentation, whenever you see an ion, be it an anion or cation, I want you to think ECG. I want you in your head to have the next formula. Ions influence ECG. Of course, when they are in balance. We have normal ECGs, but whenever you mess up with an ion to a great extent, to a severe level, especially when we're talking about sodium and potassium, You'll see it in the ECG and the presentation